Dear colleagues, my name is David Bondartsev, and on behalf of the co-authors, I will present the paper with the title Heat Exchange Crisis in Porous Structures. The development of industrial thermal power engineering, especially in the oil industry, requires intensification of processes in new high heat and high pressure combustion chambers and nozzle apparatuses of thermal power plants. The authors of contemporary works are still interested in studies of heat transfer of various homogeneous and non-homogeneous porous coating surfaces, as well as specifically designed wicks to increase their heat transfer capacity. Part of the research is devoted to thermohydraulic characteristics of boiling in porous media using thermocouple measurements and high-speed camera observation, bubble size, departure frequency, and nucleation density. The most effective and reliable way to intensify heat exchange during boiling is the use of capillary porous coatings. The main advantages of capillary porous systems are high intensity, high heat transfer capacity, reliability, compactness, simplicity in manufacturing and operation. They improve mode and technological indicators and have low capital and operating costs. Heat flows were calculated using the thermohydraulic characteristics of the boiling process in mesh porous structures obtained using photokinematographic and holographic observation. On figure 1 is laser, 2 is sine photocamera SKS-1M, and 3 is porous cooling element. In figure 2, the operation scheme of porous cooling system, the technique of the measurement of heating surface temperature and liquid consumption and steam are shown. Accepted codes: T is the tank, this the discharge, C the condensate, and CW the condensating water, and A the air. The supply of electrical energy to the main heater is carried out by TSD-type welding transformer, the output voltage of which has the following fixed values: 2.55 and 7.5 and 10 volts. The electric current powering the heater is measured according to the scheme with UCT 6M2 type plus 0.2 universal transformer. The secondary current is up to 5 ammeters. The primary current is 100 to 2000 ammeters. The heater voltage drop is measured by D523 class 0.5 voltmeter. Electric energy is supplied to the guarding heater by a VR-type voltage regulator. The TSD-type current transformer with 71 volts no-load output voltage is used in studies as the start of liquid boiling and critical loads. The current strength is regulated within the limits of 200 to 1200 ammeters. The measurements of liquid and environment temperatures are made using TL4 mercury thermometers with 0 to 50 Celsius and 50 to 100 Celsius scale and a division value of 0.1 Celsius. The temperatures of the drainage liquid and steam are measured by the chrome copper thermocouple. The cold ends of thermocouples are thermostated in melting ice. The electrodes of the thermocouple are connected with two PP63 class 0.0512-point switches. The installation and instruments are grounded to prevent the effect of induced wandering currents on indicated values of the thermocouple. The consumption of cooling and circulating liquid is determined by electric red-type rotometers with secondary electronic CSDH43 class 1 type instruments calibrated with volumetric method. The maximum possible error when determining liquid consumption by rotometer does not exceed 3%, and by the volumetric method it is 2%. The conditional permeance coefficient is further studied in literature. The spread of Kc value when integrating experimental data does not exceed 16%. The measurements and the technique for processing of experimental data are published in the works as follows from photocinematic and holographic observations, the dynamics of the vapor phase in cells of capillary porous structure after spontaneous nucleus of a bubble of critical size proceeds with the participation of the evaporating microlayer of liquid under the vapor bubble. Under certain conditions, the displacement of the liquid fume in the center of the bubble starts, followed by the development of a dry spot. Bubble detachment of bubble detachment or collapse occurs at diameters several times smaller than at boiling in a large volume, and the value of the detachment radius is calculated by the equation. After bubble detachment, also called destruction, relatively cold portions of liquid are actively sucked up under the action of gravitational and capillary forces. After some silence of the generation center, a new bubble of critical size spontaneously emerges, with growth time controlled by the coolant flow rate and degree of its underheating, decreasing and occurs with more intense heat supply from the thin, superheated liquid layer surrounding the bubble from the side of the porous structure volume. The incommensurability of the silence time with the growth period is also indicative of a constantly existing superheated pulsating microlayer of fluid, the durability and stability of which are extended by the combined action of forces. When the liquid boils in a large volume, the bubble growth stage is the combined action of forces, while in a porous system, this value could be tens of times less. The nucleation and detachment stages of the bubble are negligibly small in both systems and have the character of an explosion. The silence time in the periodic cycle of bubble formating during large volume boiling could be commensurate with the growth time of the bubble. The emergence of a nucleus of critical size in the cell structure occurs as a result of the rapid expansion of the bubble in the depression inside the liquid. However, the increasing curvature of the bubble surface slows down in its expansion in the depression, and at the initial moment the dynamic forces arising in the superheated liquid are great, which prevents further growth of the bubble. Heat is transferred mainly through the microlayer of liquid under the vapor bubble, which is cone-shaped with a dry spot in the center of the bubble. The main evaporation process occurs at the base of the dry spot. Part of the heat is transferred to the bubble from the superheated liquid in the volume of the structure. The microlayer thickness and the radius of the dry spot change insignificantly during bubble growth due to the inflow of fresh portions of coolant transported by gravitational and capillary forces, as well as due to the lifting forces acting on the bubble. The internal forces are manifested in the initial stage of bubble development and decrease before bursting. The bubble acquires a shape close to spherical, the area of the dry spot is reduced, and the shape of the microlayer changes significantly. Bubble detachment is determined by surface tension and hydrogasodynamic resistance forces, and the excess of liquid has an influence through which the underheating and flow rate of the flowing liquid is created and the control of thermohydraulic characteristic is realized. When the stem bubble does not reach the tearing diameter and its upper boundary touches the outer surface of the porous structure, the bubble collapses. A hole appears at the point of contact through which steam flows out of the bubble into the vapor volume. A wave starts to spread along the surface of the liquid. This phenomenon has been used to draw an analogy with explosive processes in elliptical systems to separate energy processes for wave energy and compressed gases. The phenomenon described was accompanied by intense ejection of liquid droplets, but no disruption of the porous system was observed. A relatively cold portion of the liquid rushes into the depression, free from the bubble, and some of the vapor there condenses until the temperature of the vapor and liquid at the boundary of their contact is equalized. In the case when the liquid excess parameter is large, all the vapor in the depression can condense and its bubble forming effect will stop. The the inflow of heat accumulated in the wall will lead to a new cycle of nucleation of a vapor nucleus of critical size. During one cycle of bubble development, the temperature of the wall below will change significantly at the stages of microfilm evaporating and cold liquid heating, which explains the high intensity of heat transfer, reduction of heat flow, value Q at high parameters of excess fluid would return the system to its previous state. Surface boiling area where GA is the Jacobs number. K is the coefficient taking into account the heat storage capacity of the wall. Equation 1 is useful for calculating cooling systems for steam turbines and gas turbines in power plants. B is area of bubble boiling developed. Equation 2. C is evaporating crisis. Equation 3. The analysis performed of the vapor bubble growth model shows that the presence of vapor on the wall should lead to an increase in the wall temperature under the growing bubble and impair its performance, but the steadily existing micro layer of liquid controlled by the gravitational and capillary forces allow to withdraw several times more heat flow under a single bubble compared to the average internal value, which generally reduces the wall temperature during bubble growth. Thus, experimental data on thermohydraulic characteristics of the boiling process in mesh porous structures, which can be controlled by the combined action of gravitational and capillary forces, are summarized. Calculated dependencies of the heat flow equation 1 to 3 on temperature presence, liquid excess pressure, thermophysical properties of the wall, orientation, geometric characteristic of porous structures, and heat exchange wall are obtained. These equations allow for calculations in the design of thermal power plants. To analyze the data and determine the limits of application of the porous cooling systems considered, taking into account the different designs of capillary porous materials, two types of evaluation criteria have been adopted. Dimensionless number, ST, and dimensionless temperature, equal to the ratio of the temperature in the nozzle trough to the temperature at the saturation line at a given pressure of the working fluid. In order to conduct a comparative analysis for combined porous system, we introduced the dimensionless criterion, the ratio of cell width of porous materials, the ratio of the cell width of the near wall layer to the cell width of the subsequent layer, area of flow values of the dimensionless temperature. At liquid side wall temperatures less than the coolant temperature at the saturation line, the coolant phase transition from liquid to gaseous state with heat absorption does not occur. Decreasing the temperature to which values is unacceptable, and when the dimensionless temperature reaches the value of 1, with prerequisites for a subsequent decrease in the wall temperature, a boiling crisis occurs. Area of moderate values of the dimensionless temperature. The area of moderate values of dimensionless temperature is the operating range for capillary porous materials. In the range of 1 to 1.3 at small values, the priority of single layer capillary porous materials becomes obvious. In the range of values from 1.1 to 1.2, this is associated with a uniform distribution of heat flow into the system of flow into the system and small intensity of the heat transfer process in comparison with a range of 1.2 to 1.25. The area of moderate values of the dimensionless temperature can be divided into 3 zones, depending on the cell width of a particular capillary porous materials, the area of small values of the width of the capillary porous materials, the area of medium, the area of the medium values, and the area of high values. The increase in the wall temperature, an increase not calculated due to system imbalance, of 1% leads to a deterioration of the heat transfer process and reduces the heat transfer coefficient by 1%. For a traditional flow-through cooling system, the allowable temperature fluctuations are no more than 10 K, with all heat flow accumulated by the wall, which leads to temperature overstress in the material of the apparatus. Any increase in temperature requires an increase in coolant flow and, as a consequence, a reliable automation system. For a porous cooling system, the maximum allowable temperature fluctuations which the cooling system compensates for independently and with a high degree of response to changes in the specific flow rate are more than 138.9 K, and the loss of heat flow will be 1.1774 megawatt cubic meters. Thank you for your attention. You can contact me via email dbondartsev@aus.kz.